Hello, everyone. Great being here at NDC London. I had a great keynote about AI development, which is a great segue to today's talk. Today, I'm going to talk about vector search and about the OpenSearch project. I'm Dotan Horovits. I'm an OpenSearch ambassador. Actually, this post is from OpenSearchCon Korea a couple of months ago. So really exciting. And I'm also a CNCF ambassador, the Cloud Native Computing Foundation. I'm also an open source developer advocate at AWS, Amazon Web Services. I also run the Open Observability Talks podcast for those who like podcasts. And you can find me everywhere at Horovits. My surname is my handle everywhere. So feel free to reach out after the talk, or if you post something from this talk, feel free to tag me. So let's talk about OpenSearch. OpenSearch is an open source platform for AI-powered search, observability, and analytics. It's a top-level project under the Linux Foundation, and the OpenSearch Software Foundation is a sub-foundation under the LF, under the Linux Foundation, dedicated for this project. And organizations such as Uber, SAP, IBM, and many more, as you can see here on the slide, have already joined the foundation and are helping us steward the future of this project. It's a massive code base, 140 GitHub repos under the GitHub org, 1.6 billion downloads to date. It's a very, very active project. As you can see, 3,000 active contributors from more than 400 different organizations. Actually, it's a top 12 most active by active contributors amongst all the LF Linux Foundation projects. So pretty cool. And actually, I added this slide just last night. A couple of days ago, AI Magazine released its top 10 vector databases in AI. And I was very happy to see OpenSearch project amongst well-established commercial products and services. So really exciting. Although, as you'll see today on the talk, OpenSearch is much more than just a vector database. So what is OpenSearch in practice? How do people use OpenSearch? So first and foremost, OpenSearch at its core is a search engine, providing highly scalable and performant search functionality for applications such as enterprise search, e-commerce search, and so on. It's also widely used for log analytics and observability. It's also used for AI and machine learning powered applications, RAG, chatbots, agentic workflows, and so on. And also it has out-of-the-box security analytics functionality. Search will be the topic for today's session. So what is search in essence? So search in essence is finding relevant documents based on a query. And relevant or relevance is the operative word here. And there are different ways to determine this relevance, as we'll see in today's talk. So search is everywhere, okay? You can find it at e-commerce, finding the right products and services for your customers' needs, document portals such as scientific articles, health records, and so on, recommendation engines. No matter what you develop, you must have some sort of an angle that requires search. And there are, broadly speaking, two main types of search. There's the lexical search and the semantic search. So let's dive into that, and I'll start with the lexical search. So lexical search, remember we talked about relevance. So in lexical search, we determine the relevance by matching words and expressions from our query to words in the document. Okay, so essentially matching words to match meaning. Let's look at this simple example. If I'm looking to buy gaming headset with microphone, that's my query string. It will look for and suggest products with these keywords and terms. So I tried highlighting the words that it will flag, individual keywords, as well as combinations, such as, for example, microphone headset, which is interesting because microphone headset in this specific combination doesn't appear in the query. So it can also provide different combinations, and that's an example of a full text search, which is one of the types of lexical queries. So let's talk about full text search. It's implemented in OpenSearch via the match queries in the query DSL, domain-specific language. And full text search is designed to handle natural language in a sophisticated way. It leverages OpenSearch's inverted index structure and linguistic processing. Essentially, it processes your text through a series of intelligent transformations. So it will go through tokenization, stemming, stop word removal, synonym expansion, all of these things that will make search more flexible and intuitive, which means that searching for running, for example, will also find ran or runs, all these variations, thanks to this flexibility. So although even if your exact phrase doesn't appear, it will still be intelligent enough to flag that document. So that's the full text search. And it uses advanced ranking through the BM25 algorithm to determine this relevance of the documents to the query. I'll talk about this based on term frequency, occurrence model of these words. I'll talk about the algorithm a bit later. So that's full text search. And on the other side, we have exact matching, which in OpenSearch query DSL comes through the terms queries, which serves a different but equally important purpose. This is your go-to approach when you need precise, structured matching. Like if you need to match a specific product ID, specific catalog number, specific error code, things like that. You don't want any interpretation. You want exact matching. This is your go-to for that. You can think about it sort of like SQL where clause in relational databases. And actually, exact matching really shines when used as a refinement tool in addition to the full text search that we saw before. So, for example, you might start with a broad full text search about, I don't know, data science documents, and then use exact matching to narrow down on a specific author, specific published dates range, or something like that. Understanding when to use each type is crucial for building effective search applications. So full text search, again, gives you these intelligent, relevance-ranked results with natural language queries, whereas exact matching will provide this precision filtering for structured data. And often the most powerful searches combine both techniques. So it's not either or. Actually, oftentimes it will be a combination of both. Also, both match and term queries offer a variety of different flavors of these queries for specific techniques available in the query DSL. So I'm not going to go over each and every one, but just to give you a sense, match queries are your everyday full text search. You want to find anything related to I don't know, Star Wars in the title. You'll run match query on the title field, something like that. And again, it has all the power of finding the variation. Like you type in dog, it will find dogs, doggy, and all these or word order variations and partial matches and so on. We have multi-match that can match against multiple fields. It can have match phrase, where the phrase does mean is significant for you. So if you look for New York pizza, you don't want it to say pizza New York in some document. You want this specific phrase, then you use the match phrase, and so on. So this is the match. And on the other hand, different terms queries exactly for these different types of exact information. The basic one is the term or terms that will match, look up specific, as we said, catalog numbers or part numbers and so on. Then you have the numeric range checks, like range, specific price range, specific date range, or not. Completeness checks, like exists, like prefix, where, you know, when you type in a search and you start typing and suddenly it starts suggesting things that start with the same prefix. This is the sort of impact that you'll have when using the prefix one. You have also pattern matching, wildcards, regular expressions, fuzzy matching, where one letter, for example, was mistakenly spelled or dropped. You still wanted to find maybe two letters. You define the distance. All of these sorts of pattern matching. This is the terms queries. Now let's see what queries look like in OpenSearch, now that we understand these structures. So essentially, OpenSearch supports a JSON interface for querying your data via RESTful API. As well as for ingestion and other operations that you can do in the RESTful API. The basic one is a simple search, like you can see here on the screen. So this is exactly what it sounds like, straightforward, efficient. You want to find matches in specific fields. This is your go-to approach. And this is the basis for the compound searches. The compound searches add Boolean operators where things get really interesting. So with this approach, we can build sophisticated queries and or not Boolean relations. For example, in this example, I'm talking about looking for documents that are about machine learning and neural networks, but not deep learning. This is the sort of expressiveness that we can get there. And in OpenSearch, what's particularly powerful about these approaches is how they can be combined. So for instance, you might start with text search to find relevant documents, use Boolean operators to refine the results, and then use simple search with filters for specific attributes. So this is where really the combination is where things become really, really interesting in these queries. Again, I'm not going through all the syntax. There are lots more things: must not, should, filters, sort clauses, aggregations. Maybe a word about aggregation. So there's metric aggregations that are more statistical functions, such as average, sum, min, max, the things that you'd expect there. And also bucket aggregations that are about grouping your data, sorting books by genre, grouping products by price range, grouping your logs by date range. These are the sorts of bucket aggregations that you can do. OpenSearch returns results ranked by their relevance, okay? And it uses BM25 algorithm to calculate the relevance of these search results. Don't be alarmed by the formula. I'm not going to go into that, so you're not back to high school. But just the essence of the formula is to show you that it considers multiple factors. It considers how often the terms appear, how unique they are across all the documents, the document length itself. All of these help determine which results are most relevant to the user's intent. Remember, in lexical search, we determine the relevance by the words, their frequency, their occurrence model, and all of that. So this is lexical search. Each result gets this ranking score attached to it, leveraging Apache Lucene engine. In addition to the RESTful API, OpenSearch also has a UI frontend called OpenSearch Dashboards, where you can run queries and examine resulting documents visually. That's what you see on the left-hand side, the Explore view. And also you can build dashboards and visualizations around your data, such as in the right-hand side. You can also define alerts, manage teams, workspaces, and a lot more through this UI. It will be less the focus of this talk, but just wanted to mention the UI is definitely a powerful tool here. OpenSearch is built for scale and resilience. So I'd like to zoom into the distributed in-memory architecture that enables that. Okay? So the main top-level concept is index. And an index in OpenSearch is a bit like a table in a relational database. This is where you store or index your data, your document. But actually, that's just what your application sees. Under the hood, internally, the index is a logical namespace, if you will, that points to multiple shards, potentially multiple shards. And this allows the use of a scatter-gather or a map-reduce pattern for running efficient parallel search. So when a search request comes to the client, it reaches a coordinator node that evaluates which shards are relevant for this, needed for this request, then sends a shard-level request to the relevant shards. Then each shard receives the request, executes the request locally, and returns the results and the coordinator merges all these responses and then returns the aggregated result back to the client. So, and the shard is actually an instance of Apache Lucene. How many know Apache Lucene, open source library? Okay, we have a few. So it's an open source under the Apache Software Foundation, a very established one in the world of search, and it's a fully functional search engine in its own right. So you may say that each shard is a fully functional engine in its own right, and Lucene Index is the underlying data structure for lexical search with inverted index, posting listings, and other supporting data structures. And again, not to be confused with the OpenSearch index, which is the top-level table, if you will, and the Lucene index, which the index that maps to the individual shard. So an OpenSearch index could consist of a single shard, but generally consists of several shards to allow the index to grow and split over multiple machines. Another point about shards, each primary shard can have one or more replica shards that hold a copy of the data for high availability, as well as for to speed up search. So it's not just a passive standby backup, it's also for serving reads. So each shard contains multiple segments, where the segment is an inverted index. So a search in a shard will then search each segment in turn and combine the result of into the final result of that shard. Segments are immutable, so when you write a new document or you update a document, it actually marks the old one as deleted, indexes a new one, essentially, and the old one will then be purged as part of the merge process. So that was about lexical search. Lexical search, as we saw, searching for keywords. It's fast, it's accurate, it's very, very robust. We've been doing it for a few decades now. And when I'm looking for things, like when I'm looking for books about Martian or any variation, Martians and something like that, this is my go-to tool. But lexical search lacks the semantics of the meaning and intent of our query. For example, let's say if I'm looking for aliens, whether Martians or others, or maybe the folks there on the picture, who recognizes? Let's see who is old enough to recognize. Yeah, so if I search for aliens, will it find Alf? Or will it find the ET? Or will it find the Martian? This is where semantic search comes into the picture. So let's look at an example. Let's search for sailboat shoes. So you can see the two queries side by side in OpenSearch. On the left-hand side, you see the match query that we already met for lexical search. And on the right-hand side, you see a neural clause for neural search, for semantic search using a given LLM, a machine learning model, and both searching for the same term, sailboat shoes. As you can see on the left-hand side, the lexical search returns, let's see, sailboat decoration, sailboat pendant, girl's sailboat dress, sailboat earrings. Not exactly what we intended, right? And on the right-hand side, we see much more relevant, many more relevant results, sailboat shoes. So that's just to get you the sense of where semantic search shines. And we can see the search evolving from lexical search based on keywords into semantic search based on meaning and intent. And with the wave of semantic search and the growth of LLMs, we've been seeing multiple new search paradigms around that, including multimodal search, sparse search, conversational search, and more. I'm happy to say that OpenSearch supports all of these. So I want to look into semantic search with dense vectors. So in semantic search, we encode the data as vector embeddings and run the searches on the embeddings representation of our data. A vector embedding is a vector in a high-dimensional space, capturing this deeper patterns and similarities in the meaning, context, and the structure of your overall data. So you give it some text, for example, and the resulting embedding will be a series of essentially floating point numbers for each of the dimensions. So if you have 300 dimensions, you'll have 300 floating point numbers. And by the way, 300 is a very modest number. probably your LLMs that you use are an order of magnitude at least more than that. And these embeddings are generated with machine learning models, with LLMs. It could be small models. They use deep neural networks to understand the meaning and context of queries and create these dense vectors. That's why it's also referred to as neural search, because of the neural networks involved in the process. And the semantic similarity is manifested in these various dimensions. So I try to illustrate that so that you see that all of the things that are about cities will have certain dimensions that will manifest that, others that are about animals, other dimensions. So this is how, for us humans, it's a bit helpful for oversimplifying it, but just to get a sense of what it means. And it's important to say, choosing your embedding model, the LLM or machine learning model that you use, is a crucial decision. There are multiple models out there, as you might have seen, and they're yesterday there was a talk about vector databases, and someone asked, how can I figure out? So there is an embedding leaderboard on Hugging Face, MTEB, that I think is very, very useful because it lists that, and it has the different dimensions and parameters that you can factor depending on your trade-off. So things such as whether, how the memory usage, the number of parameters, the embedding dimensions, things such as what kinds of machine learning algorithms it's best supported, like classification, clustering, re-ranking, and so on. So it's a good place to start, at least, to try and narrow down which models might be good fit for you in your trade-offs of performance, memory consumption, and latency, and so on and so forth. And it's not just about text. Unlike lexical search, in semantic search, embeddings can be generated for different modalities. It can also be generated for images, for video, for audio, even for PDFs that are themselves multimodal. Because if you think of the typical PDF, you have, let's say, a chart, you have a table, you have a header, you have a paragraph. Each one of these requires different machine learning logic to extract the meaning out of it, right? Extracting from table or from a chart is whole different than a paragraph. So there are different machine learning embedding models for different modalities, and also multimodal models that can map different modalities onto the same vector space. So in our example of sailboat shoes, the string sailboat shoes, the text, and an image of a sailboat shoes should be close together on that multimodal space if you choose the right model for that. So we talked before about lexical search, where we use BM25 algorithm to calculate the relevance based on the term frequency and occurrence model of the words in the text. With embeddings, similarity is calculated as proximity in this multi-dimensional vector space. So essentially taking the embedding of your query and finding the vectors, the embeddings that are closest to it in this multidimensional space. So let's dive deeper into what this proximity means. And the first question is, how do you even measure distance in this space? And there are different ways to measure that. There's a Euclidean, there's a cosine, inner product, Hamming, and many others that OpenSearch supports. I'm not a mathematician. I'm not going to go into all these fancy formulas. The main takeaway is that each distance calculation method has its own advantages based on your use case. Some are better for recommendation systems, some for document classification, and so on and so forth. So this is a decision probably that your search engineer or your ML engineer will take when designing the system in the very initial architecture design. And once we determine the space, we can run the algorithm to find the k nearest neighbors, KNN algorithm. The exact KNN is a brute force algorithm. It essentially runs exhaustive comparison to every single vector in your database, which of course guarantees the most accurate nearest neighbors. But on the other hand, it scales poorly to large data sets and high cardinality, many dimensions, which makes it impractical to many use cases. And in these use cases, we use approximate KNN, or sometimes it's called ANN, which trades some accuracy for much faster search time. So essentially trading off recall for latency or QPS, queries per second. And there are different algorithms that implement that. The popular ones are AgenSW, a hierarchical navigable small world, and IVF, inverted files. And there's also different engines that implement these algorithms. OpenSearch supports several open source engines. First, Apache Lucene that we talked about before. So many know Apache Lucene from lexical search. Apache Lucene also has capabilities in vector search. And also FAISE. FAISE is Facebook AI similarity search. There's also a plugin for JVector, different types of engines. And again, when you design, the initial design, the different engines provide different sets of capabilities. So for example, Lucene allows partial loading of the vector data, supports score-based retrieval, while FAISE loads the full index into memory. On the other hand, FAISE supports SIMD vectorization and distance calculation, supports GPU-based acceleration in the indexing. So different trade-offs. I would say Lucene is memory efficient but doesn't scale very well. So FAISE would be suitable for the large-scale use cases, let's say tens of billions of vectors and above, whereas Lucene is a good option for the smaller deployments, but then has this, for example, intelligent filtering strategy, where the determining whether to use pre-filtering, post-filtering, exact KNN will be chosen for you automatically based on the situation, so you don't need to define it in advance. By the way, we also recently introduced Lucene on FAISE, which opens up the option of best of both worlds. It's very, very new, so I'm not going into that, but if you are deep into these areas, do check it out. And of course, we're happy to get feedback on this new feature in the open source. So you can use OpenSearch as a simple vector database. You saw it was ranked 10 top in the 10 top vector database. That's using a straight up vector database. You store your raw vectors. You see this array of floating point numbers. So you write your document as embeddings already. So you write the embeddings of your documents, then into a KNN index. So note that this is a KNN index, is the underlying data structure, not the Lucene index we talked about before. And after you have the vectors of all your documents indexed, then you provide the vector of your query. And OpenSearch can then run the algorithms, all the calculations we talked about, to find the nearest vectors and return the vectors to you. However, if you use it like that, obviously it's up to you to transform your data, your documents, into vector embeddings for ingestion. And then you also need to transform your query into a vector so you can run the similarity search. And then when you get the resulting vectors, you need to then transform them back to the original data, right? Because that's what you care about, essentially, the resulting documents. And then what if the text is too big for the model or things like that? Most engineers don't know how to do that and frankly don't want to deal with that. They want, instead of that, they want that. They want to put their data as simple text, PDF, images, whatnot. Then they want a simple text query to ask about the data and get the documents back. Essentially, they want semantic search experience. And that's exactly what OpenSearch provides you. It takes care of all these transformations from data to vectors and back to data and many other things, as we'll soon see. Takes it for you so you don't get to deal with that. And we're all engineers, so let's dive deep, open the hood, and see how it works under the hood. So you send your data, we're starting from left to right. You send your data with different modalities, text, audio, video, PDF documents to OpenSearch core. Then it undergoes text chunking, which involves splitting long documents or text passages into smaller segments to improve the search retrieval and relevance, because ultimately, first of all, most embedding models have token length limitation. So if your data is too big, you will have to chunk. Sometimes it's also better for you to chunk in terms of relevance. So chunking helps maintain the quality and relevance of the vector search results by ensuring that each embedding represents a focused piece of content that fits within the model constraints. So OpenSearch offers this text chunking pre-processing step. And after that, the ML embedding model is used to generate the embeddings. And then OpenSearch Core indexes that, stores that, and then it's available for your search applications. In terms of scale, OpenSearch is scaled from billions to trillions of vectors. That's the scale. On the other hand, indexing embeddings can quickly become both time-consuming and costly in these scales. So with traditional CPUs, at least. So in order to solve that, we've released GPU-based acceleration for indexing the embeddings. Again, everything is in the open source, of course. And then once we have the data there, we can use neural clause for KNN search. You just write your query as text, as you can see on the left-hand side. And then a similar process will convert the query into an embedding using the same ML embedding model, and then run the KNN search algorithm for you to find the similar embeddings with their respective relevance score, and return the respective documents of these embeddings to you as a result. So again, as you can see, side by side, both the query and the response, you don't see any of the embeddings. The query is text. You get the document back. You don't see all this embedding stuff when you actually interact with searching. OpenSearch provides clients in many programming languages, such as .NET, Python, Ruby, PHP, Go, and many others. I know that many here in this conference are .NET folks, so I did highlight the .NET one. There are actually two clients, .NET clients. One is a low-level one called OpenSearch.net. The other one is a high-level abstraction, OpenSearch.client. And you can use both clients in console programs, .NET Core, ASP.NET, worker services. So definitely give it a try. You can use search pipelines to build or to reuse existing result re-rankers, query rewriters, and other components that operate on queries and on their results. I'm not going to that. That's a bit more sophisticated. But just so you know, search pipelines make it easier for you to process search queries and search results within OpenSearch. So you essentially offload some of this logic from your application to the pipelines, which simplifies your application code. And the performance also. And as part of the search pipeline, essentially, you specify these list of processes, and then you can easily add or reorder them to define your logic for processing either the queries or the results. And similarly, by the way, there are also ingestion pipelines that you can define. Again, I'm not going to pipelines in this talk, but just so you know, very, very powerful part of the OpenSearch platform. OpenSearch supports many pre-trained models. For example, there are about a dozen text embedding models that are available out there, also open source in Hugging Face. And you can also upload and serve your own custom ML model if you locally in OpenSearch for your specialized use cases. But what everyone asks, what happens if I want to use one of the fancy, shiny LLM services out there, right? Because this is the power of this era where we have so many powerful models out there that can boost our search relevance. And they come out every day, essentially. So how do you manage that rate of innovation? OpenSearch offers easy integration to all these models through ML Commons, which is an ML-based library with blueprints that allow you to easily develop new connectors to all these LLMs. So you can already find some that the community has developed for OpenAI, Cohere, DeepSeek, and so on. But it's very easy to also develop for any other model that you find relevant for you. Actually, when DeepSeek came out, it took the community 2 days to release the connector for it. So that's how easy it is once you get the hang of it. Now I would like to talk about cost, because the vector search workloads are heavy on memory. Let's look at a typical example of encoding a 100 megabyte document into a vector embeddings with OpenAI. So OpenAI's text embedding 3 small generates 1,536 dimensions, each stored as a 32-bit floating point, so 4 bytes. That's about 6 kilobytes per vector. And now we take this 100 megabyte document that we have, chunking it to 100,000 segments. In the chunking process, we'll need around 600 megabytes of embedding data. That's 6 times the size of our original document. And that's, again, nothing to do with OpenSearch or any vector store. This is just essentially invoking the ML model. So OpenSearch offers several ways to optimize that. First, in the level of the basic ANN algorithms. We talked about AgenSW and IVF. There are different parameters that you can tune. Secondly, for low memory environments, OpenSearch provides disk-based vector search and also derived source options. And on top of these, OpenSearch provides a what's called vector quantization, which essentially you can think about like a compression mechanism for your vectors that essentially trades off some accuracy in return to reducing the memory requirements by at least 2 times, but you can get into 32 times depending on the technique, as we see here. So essentially there are different quantization techniques to choose from in OpenSearch based on your data and the trade-offs. With scalar and binary quantization, we reduce the dimension size from 32-bit or 4 bytes floating point to 2-byte floating points to 1-byte integer, or maybe even to 1 bit binary, if again based on your relevance and your data. And that's for each dimension. So multiply that by the number of dimensions in your space. And the product quantization actually reduces not the size of the dimension, but the number of dimensions. So let's say from 128 dimensions down to 8. So these are the types of quantization that you can do. Sometimes semantic search alone isn't enough. Semantic search is great for understanding intent in a natural language, but it may miss important keywords, especially in fact-based search. And this is where hybrid search can help us. Now I leave you in suspicion just so that I can take a sip. Now that you're fascinated, let's see what hybrid search is. So hybrid search combines lexical with semantic search, that is keyword-based and vector-based, dense vector-based, to improve search relevance. This approach ensures that the results include both exact word matches and conceptually similar context. If we look at the hybrid query, essentially it's comprised of subqueries of the types we already know, right? So you can see the match clause for the lexical search and the neural clause for the semantic search, for the neural search. But how is it actually executed? Again, let's look under the hood and understand how it works. So each query of the different subqueries runs through its own regular path, as we've seen before, to find the relevant results using the respective algorithms and engines for them. So let's say BM25 for the lexical search and cosine score for the semantic search. And it's important to say that different engines use different scoring mechanisms and ranges. For example, Lucene lexical search query will return a score between 1 to infinity, and FICE with AgenSW will return scores between 0 and 1. So then we run rank normalization to adjust the scores produced by the different engines and algorithms to a common scale. Okay? And once we have the common scale, then we combine the results of the different subqueries to a unified score. We can combine them with one of 3 techniques. We can do arithmetic mean, geometric mean, or harmonic mean. And we can give weights to the different subqueries. For example, in this example here, on the right-hand side, I actually I use arithmetic mean, and for the combination, and I give more weight to the neural search over those of the lexical search, so 0.7 and 0.3. And once we have the combined score, OpenSearch fetches the original documents and returns the unified result list with the normalized scoring. Again, there are different normalization methods and techniques that you can use in OpenSearch. Essentially, normalization techniques are broadly divided into two categories. There are the score-based normalization and the rank-based normalization. The score-based normalization works on the raw score, whereas the rank-based normalization focuses on the relative order of the results. And OpenSearch supports, as I said, multiple normalization techniques. You can see some here, like the L2, min-max, recently added z-score for score-based, and also RRF, reciprocal rank fusion for rank-based normalization. Not going, again, into the math, but important to say that each technique has its own advantages based on your use cases and the individual scoring algorithm that you need to combine. Of course, the primary question for a user of hybrid search is how the heck should I choose the normalization and combination techniques and the weighting parameters that would be suitable for me. And the problem is that what's best depends strongly on the corpus, on the user behavior, on the application domain, so there's no one-size-fits-all answer that we can provide. So in OpenSearch 3.2, recently released, we released Hybrid Search Optimizer, which provides systematic approach with a graphic tool in OpenSearch dashboard. So it treats hybrid search configuration as a parameter optimization problem, essentially, and search engineers can then define a query set, judgments, and their quality metrics, and then run sort of experiments via this tool to find the parameter set that yields the best results based on their quality metrics that they define. So probably search engineers that will do it in the, as I said, design phase, but a very, very powerful tool that comes out of the box as part of the OpenSearch project. We talked about neural search with dense vectors, and now I'd like to talk and present sparse vectors and neural sparse search, which offers a budget-friendly systematic search alternative using lexical search with semantic tokens. So in sparse encoding, we use the text to create list of tokens with tokens that have similar semantic meaning, and also we use specialized machine learning models to do that. I'll talk about the models in a minute. So if you remember, in dense vectors, documents were presented as a high dimensional vector embeddings, and to search them, we needed to use KNN index as the underlying data structure. In contrast, in sparse vector search, in neural sparse search, we can actually use the native Lucene index to run the search, because sparse encodings are essentially vectors as they are used in keyword-based search in Lucene. So that's the beauty. So compared to KNN indexes, sparse embeddings are more cost-effective, both in smaller in the index size, the RAM cost is much, the runtime RAM, the computational cost, all of that is much more reduced. So let's look at an example how it works in practice. So actually yesterday on the talk that I heard, someone talked afterwards about Apple, so I gave this example. Let's look at an example where two documents refer to the word Apple, but with different semantic meanings. So document 1 talks about Apple products are expensive. Document 2 is an apple a day keeps the doctor away. And as you can see, the text expansion, this is the learnable term expansion, this is the formal word in the industry, so adds tokens based on the semantic meaning, and also weights each token for how relevant it is compared to the context of the original term. So you can see in the example of document 1, added terms such as cost, budget, iPhone, and so on, which are related, of course, semantically. And document 2 has fruit, medical, diet, and other tokens, again, based on the semantic meaning. These weights are generated within the text expansion, and they're being used to score the document and the query. So the query undergoes the same term expansion process. And the term expansion uses neural sparse encoding models, machine learning models that are used to transfer the text into these sparse vectors and then to also convert them into these token weight pairs representing the entries within the vector. And note that while we do use machine learning models for the text expansion and the weighting of the tokens, the resulting sparse vector is actually stored in a regular Lucene index, not a KNN index, and uses a standard BM25 algorithm for ranking them. So again, we get the BM25 that's fast, accurate, and very memory efficient. The matching score for the entire query and the document is essentially the dot product sum of all the scores of the tokens that appear in both the query and the document. So this helps boosting the most relevant features or terms in your document and discard the less relevant ones. So in this case, you see the doc1 is more relevant to the query Apple headphones than document 2, as we would also intuitively understand from the semantics. And there's an algorithm, for those who know a bit or heard the buzzword about seismic algorithm. This is the algorithm that makes sparse vector calculations very efficiently at scale. OpenSearch supports many pre-trained sparse encoding models. Actually, OpenSearch open-sourced sparse models that you can use out of the box without any fine-tuning, also available on Hugging Face. You can use them also for other contexts outside of OpenSearch, of course. In fact, I think the OpenSearch sparse models are the most popular and downloaded sparse encoding models in Hugging Face. And there are different model types depending on whether you want the term expansion performed only during document ingestion or also on search time, trade-off of accuracy versus performance. So again, just to summarize, Neural Sparse Search offers lexical search with semantic tokens. It's a lightweight, if you will, semantic search over Lucene index and BM25 for cases in which dense vectors are too resource consuming and where your data is not overly big, so not the billions and the trillions scale. And also, by the way, interestingly, sparse encoders perform better on unfamiliar data sets. So if you have data sets that your pre-trained models, regular models don't know, actually this can actually perform also better in the relevance. So there's more. I won't be able to cover all of that in this talk. I think we're reaching the end soon, but I did want to cover give you a taste of some more relevant things. So first of all, several popular LLM frameworks integrate with OpenSearch as their vector store or semantic cache to build knowledge-powered conversational applications, AI agents, RAG applications, retrieval augmented generation. So if you work with LangChain or Llama Index or any of these, just go to their tech docs and see how to integrate with OpenSearch as your underlying vector store or semantic cache. Also, OpenSearch offers a rich agentic AI framework for running agents locally as well as serving external agents. OpenSearch has multiple built-in agent types, from running simple sequential flows all the way to complex plan, execute, reflect, and multi-agent flows. The later two, by the way, were added in version 3, the major release. A lot has happened in this space in V3. This portfolio of agents is suitable for a variety of AI tasks, including RAG and the chatbots and research and the automated RCA, root cause analysis. So really, really cool stuff. And it offers persistent agentic memory, both short-term for session-wide or long-term cross-sessions, as well as a suite of agentic tools that agents can invoke. I wrote a blog post about this. I know that I'm just touching very briefly, but if you scan the QR code, I have a whole blog post dedicated just for this, because it's a topic of a whole dedicated talk on its own. OpenSearch v3 also introduced native MCP support, Model Context Protocol, for standardized integration with external AI agents. So MCP is essentially an open, for those who don't know, open protocols that standardizes the communication between agents, tools, and data sources, essentially. So starting with OpenSearch 3.0, we have already built-in MCP server that exposes operations such as searching indexes, pulling index stats, and so on as tools, making it easier for external agents to interact with OpenSearch, whether Anthropic or OpenAI or whatever you use. And then with MCP client support, users can incorporate their existing tools and systems into ML Commons agent framework that we talked about before, enabling more comprehensive and customizable AI-powered solutions. As you heard, a lot happened in V3, the major release that we had about half a year ago. So if you want to hear more, I had a whole episode on my podcast, Open Observability Talks. I actually hosted the governing board chair, Carl Meadows, and the release lead and the technical steering committee member, Pallavi. So if you want to listen to that, scan the QR code, a fascinating episode, a good listen on the road and the ride back home from the conference. They gave good insights about V3 and about the roadmap and vision and a lot more about the community. So let's summarize what we've seen. We've covered many topics on this talk about search. First of all, we talked about lexical versus semantic search, so keyword-based versus meaning and intent, and how to derive similarity. How do we derive relevance? What's relevant based on keywords or based on meaning and intent? On lexical search, we talked about full text search versus exact search. Remember the match queries and the term queries in query DSL syntax. We talked about compound queries, aggregations, faceting, fuzzy matching, a lot more. That's on the lexical search. On the semantic search, we talked about dense vectors, lots of terms there as well. The embeddings, we talked about spaces, KNN, ANN, approximate KNN, different algorithms, engines, modalities, chunking, and so on. We talked about multimodal search, so not just text, but also images, video, audio, PDFs. We talked about hybrid search, which gives us sort of the best of both worlds, semantic and lexical, and the different normalization and combination techniques that we can use to tune that. We talked about neural sparse search that allows us running lexical with semantic tokens. We talked about agentic search with agents, tools, MCP, and so on. We saw how OpenSearch provides this end-to-end search experience across all these types of search. We saw how it's performant and scalable by design. We talked about this distributed in-memory architecture, replicas, shards, and so on. We saw how it leverages the best-of-breed open engines, frameworks, protocols. We talked about Apache Lucene, about FICE, about MCP, and so on. We can plug in our own model of choice. So you have your own model. You just use the ML Commons library and the plugin and the connectors to use that. We can integrate with agentic AI workflows, both built-in and external. And very important, maybe because I'm an open source aficionado, but it's open source, it's community-driven, it's production-ready, and it's foundation-led under the Linux Foundation. So where can you learn more about that? Of course, on the GitHub organization. Again, 140 different GitHub repos there. There's a very active Slack instance that you can join the community there. There are forums, there are user groups, actually around in 19 countries already around the world. We actually have a user group here in London for those who are London-based, and also one in Bristol, if we talk about the UK. There are the regional events, OpenSearch Cons. So OpenSearch Con Europe last year was in Amsterdam. This year in April, it's going to take place in Prague. So if you're interested in that, this is the place to be. A couple of days, all the maintainers, governing board members, technical steering committee members, technical advisory group members. I'm one of the leads of the observability technical advisory group. I'll also be there. That's the place to hear to interact, to ask questions, to learn more, and to get involved. I've put all the useful information in one link. It's like a page that I maintain with all the useful links that I see people looking for. So if you scan the QR code, you'll get to my page where I just have all these links and also additional, like the roadmap, like their online playgrounds that you can play with that without installing anything, their tech docs, and many others. So again, one QR code to give you everything in one place. And of course, I'm happy to chat, answer questions, and also I have cool OpenSearch stickers that I'm happy to give. So I'm Dotan Horovits. Thank you very much for listening, and happy to meet you.